Right, so this test is on power and efficiency. So this part as well is really important throughout the syllabus. So you need to have a perfect understanding of these power and efficiency concepts as well, right? So we'll move on to the first question. Consider the units below. Units of power are. So you know that power is work divided by energy, right? Work measured in joules, work divided by time, right? Work measured in joules, time, seconds. So joules per second or watts. That is how we measure the power. So I'll just explain each unit. So first unit is given as kilowatt hours. Kilowatt hours. So you might think that because this includes watts, this should be a unit of power. But let's see whether it is the case. Kilo means 10 to the power 3. Watt means 1 joules per second, right? Hour means you can write it in terms of seconds. So this second cancels off. Then you get 3.6, 10 to the power 3, 10 to the power 3, 10 to the power 6 joules. So it is a measure of energy. Kilowatt hours is a measure of energy, not a measure of power, right? So usually the electricity consumption is measured using kilowatt hours, usually, right? So in the home, you are charged for the kilowatt hours. It is not a rate of work or energy. It is a amount of energy. So it is measured in joules. So it is not a measure of power, right? Then the another unit they have given is electron volts, electrovolt. So mostly we use this when we are dealing with atoms and energy levels of atoms, right? You will learn this in matter and radiations. Mostly you will learn this unit in matter and radiation. I'll just briefly explain this. Simple E means charge of an electron. So charge of an electron is this much, coulomb, right? Charge is measured in coulombs. Then you have volts. So 1 volt, this is very important. It is better to remember this. Joules per coulomb. You will learn this about in electric fields. So just for now, just remember 1 volt is equal to 1 joules per coulomb. So if you substitute it here, you can see coulomb cancels off. Again, you end up with joules. So this much of energy is what we call a 1 electron volt, right? So when you are dealing with the energy levels of an atom, you oftentimes use these electron volts. So that also is not a unit of power. Then you have joules per second. So joules per second is obviously power, right? 1 joules per second is equal to 1 volt. Sorry. 1 joules per second is equal to 1 watt. Right, second one, energy generated by 500 watts microwave oven within 5 minutes. So the oven has a 500 watts, meaning 500 joules per second. So this is used within 5 minutes. 5 minutes means 5 times 60 seconds. 5 times 60 seconds. So you can use this. You can think these questions in terms of energy as well, right? I mean, if you need to get energy, you need to you have to make sure that you are multiplying watts by time, right? This is watts and time, then you get energy. So this is the equation. Power is equal to energy divided by time or work divided by time. So energy is, you can use this equation as well, right? P times T. You can make sure that you are using the correct equation by thinking about this energy, right? I mean, thinking about the units. Per second, second cancels off. So 2500, sorry. So this is 15, sorry, 13, and 30 times 5 is 150. Then you have 3 zeros. Instead of 3 zeros, you can 10 to the power 3, you can use kilo. Then you have 150 kilojoules, right? So the answer should be fourth one. So these are like the order of calculations also is important, right? If you like multiply 5 by 5, 5 times 5, 25, 25 times 6. Rather than doing that, it is better to do like this. 5 times 6 is 30. 30 times 5, easily you can say it is 150, right? So when you're doing those calculations, you have to think about an easier way, more convenient way to do that calculation as well, right? So you have to get used to those methods. So this one is not that complicated, but even if you get a complicated calculations, be mindful whether there is a way to do that calculation simply, right? That's why because students go for like really complicated methods when you are doing calculations. That's why they say that time is not enough for the questions, right? So you need to have that practice as you are doing these calculations. Okay, right. Third one, power consumption of a country is 40 gigawatts. 40 giga means what? You need to remember these values of these prefixes. Giga means 10 to the power 9, right? So this is the power consumption of the country, meaning per second this much energy is consumed. Then they say 1 kilogram of coal, 1 kilogram of coal provides 20 megajoule. Mega means 10 to the power 6 joules. So whenever they say, we call this a calorific value of a fuel. So that calorific value, you can write it like this, 10 to the power 6 joules per kilogram. Per kilogram, this much energy. So this is the calorific value of coal, right? Per kilogram, this much of energy. So students find sometimes, some students find that difficult whether to multiply or divide or something like that. So when you face, when you cannot figure out whether to multiply or divide, always make sure when you get a question like this to think about the units. Units should be matched at both sides, right? So if you get the units correctly, then you can figure out whether you have to multiply or divide these values. Right? Okay. Right. So we have this much of a power. So power generation is, this is joules per second, okay? Joules per second. So what they ask is rate of coal burnt, rate of coal required per second. So let's say that is, let's say m dot. M dot means m divided by t, right? Rate of mass. So the units is kilograms per second here. Okay. So you know that this should be matched with this side. So you can say you have to multiply this 20 times 10 to the power 6 joules per kilogram. So you can see if you multiply these kilo per kilogram, kilogram cancels off. Per kilogram and kilogram cancels off. Then you end up with per second, right? Per second. Then you just have to find this m dot. I mean per second per joule, joules per second, right? I mean, so unit of this one is kilograms per second. Kilogram cancels off. You get joules per second. Joules per second means watts. Okay. So 20, 2, 10 to the power 6, you get 10 to the power 3. So you get 2 times 10 to the power 3 kilograms per second. So this is m dot. 2 times 10 to the power 3 kilograms per second. That is the rate of coal required in order to generate this much of energy, right? Just make sure that you are getting the units correct if it seems complicated, right? So the answer should be third one. Right, fourth question. Within the time that an old car initially at rest accelerates and achieves speed v, initially 0, then it gains a velocity v and it accelerates mass within a simple t time, right? A new car with the same mass accelerates and gains a speed 2v. You have a new car and 0 and here, but it gains a velocity 2v within the same time. So this is one case. This is the another case. What they ask is power ratio between old car and the new car. Power ratio between old car and the new car. Right. So you know there's an equation to use this one, right? In the theories you have learned this. P equals Fv. But remember that you cannot apply this equation because for this case, velocity is increasing. It is not constant. You can apply this only for constant velocity, Fv, right? Only for constant velocity, and if you are going to apply for instance, you can apply this, right? You can apply for a range. You cannot apply that when there's an acceleration. You cannot apply that. So you can here you can't apply that. It is only for instant or for constant velocity, right? So you cannot apply this. So how do you use this? So the power, you can find power here. Kinetic energy gained, that is energy divided by time. So the energy gained is half mv squared minus 0 initially at rest and divided by t. So using this one, you can find the power here. So you get mv squared divided by 2t. So that is P1, right? mv squared divided by 2t. Okay, then the second case, let's say power is P2. For that one also m, but now the velocity is 2v. 2v squared minus initial velocity c, kinetic energy 0, divided by time. So you get m here 4v squared divided by 2t. So now you have to get the ratio between this one and this one. So what's the ratio? P1, P2. So you can get rid of these constants, right? V squared, m and t. You can simplify this to 2. So you get here P1 is ratio value is 1 over 2. Here the value is 2. Then cross multiply by 2, 1 is to 4. So this is the ratio of power, P and P2, right? You can easily do this. You don't need this much calculations. This is just for the explanation, right? So you can easily see that if the velocity is 2 times the previous case, the power should be 4 times. If the time also is the same. Because V gets squared. So 2V gets squared, right? Which creates 4. So the factor would be 4 there. 1 is to 4. Right? You don't have to do this much calculations. This is just for the explanation, okay? Okay, fifth question. A load 400 kilogram is lifted. So this has a weight 4000 Newton. Is lifted at constant velocity 2 meters per second. Power provided by the train is, so the uh, so the crane is the what provides this tension, right? Tension force. So it is work done by the tension regarding the power. So you know that this is a constant velocity. So whenever that is the case, so the which drives this motion is this tension. So we can say this is the driving force. Since the velocity is constant, you can simply use this equation, Fv. So force required is, to move this at 4000 Newton. Driving force also should be 4000 Newton because constant velocity, right? So the driving force is 4000 and the velocity is 2. So easily it is 8 kilowatts. 8000. Put a K there. In the answers it is just 8000. So the answer should be 4. Right. 6. Maximum speed a car can move when the power of its engine is 24 kilowatts, subjected to a constant resistive force of 800 Newton. Okay. So here you have the car and 24 kilowatts. That is the power of the engine when it moves at maximum speed. Resistive force, they have given a resistive force 800 Newton. So here also you have to understand that Vmax, if the car has a maximum velocity, its velocity cannot further increase. So it has to move at constant velocity once it reaches the maximum velocity. So for this case as well, you can use this equation, P equals Fv. But here the F is driving force, right? So we understood that this is moving at constant velocity. So the driving force also should be equal to the resistive force. Forces should be balanced if it needs to moving at constant velocity. So force, so this also should be 800 Newton times velocity. So that is what we need to find. And the power is given as 24,000. 8, 3, 2, 30. So the Vmax is 30 meters per second, right? So the car moves at this speed, right? So the answer should be fourth one for the sixth question, right? Seventh question. When a boat is riding on sea at 5 kilometers per hour, 5 kilometers per hour. For this question, I'm not going to convert units, right? And the power of the engine is 500 watts. Subject to a constant resistive, they say the resistive force is proportional to square of the speed of the boat. So let's say this is the resistive force, capital R. If it is proportional, you can put a constant there and you can write V squared. So this is the resistive force is kV squared. Okay. So at the second case, they say power required if the speed of boat is increased to 10 kilometers per hour. So at each cases, the boat is moving at constant velocity. So you can use P equals Fv, right? Right. So for this case, I'll just apply P equals Fv. So the P is what? 500. Then we have a F here and a R here. If they are moving at constant speed, These two are equal, right? So let's say like this. If resistive force is R in this first case, what should be the resistive force here? So you can see speed is doubled here. So if speed is doubled, that times 2 squared. So the resistive force should be 4 times the second case. So at the second case, resistive force should be 4R. Driving force also should be 4R because moving at constant speed. Right? Understood? Because they say resistive force is proportional to velocity squared. So if the speed is doubled, resistive force should be 4 times. Okay, I'll just apply it here. For the first case, driving force is, I can use that as R times velocity. Velocity is actually 5, right? To be more precise, you have to put a proportional sign here because I substituted 5 here, right? It doesn't matter because it's MCQ. Then I'm going to apply equation here. Let's say that the power required for this is what they ask. Let's say that is P dash, P prime. So it is equal to force is now 4R times velocity is 10. Okay. So from here you can find R. So it is 500 divided by 5. So it is 100. Okay. So this is 40 times 100. R is 100. So you get 4,000. 4,000 watts. 4 kilowatts. So that is the power at the new case. Okay. It takes time to explain, but you can quickly get these answers, right, for an MCQ. You have to think about the proportionalities here actually. So here there's a slight difference because I didn't convert these kilometers into meters per second, right? It is not necessary here because when you are substituting, those units cancel off, right? So basically what I'm using that there is a proportionality. To be more precise, it's better if you use proportionalities here because if it is a MCQ, sorry, if it is a essay question, you have to use a proportionality, right? Proportionality sign here because you are substituting a kilometers per hour there. Right. So it is 4 kilowatts. Fourth one, right? Right. 8. When a car weighing 1,000 kilograms moves at constant speed 18 kilometers per hour. So I have to multiply this by 5 over 18 in order to make it meters per second. So it is 5 meters per second, right? Moving at 5 meters per second. So for this, power generated by the engine is 20 kilowatts. So this is the power generated by the engine. If the resistive force on the car does not change when the power of engine is increased to 25 kilowatts, acceleration of the car is, right? So they say you just increase the power to 25 kilowatts. Here 20, you increase the power 25 kilowatts. So you can see if it is moving, initially it is moving at this speed. So to move that speed, there's a driving force. and there's a resistive force as well. These are equal, right? Because need to have the constant speed, 5 meters per second. This is the resistive force. So using this one, I'll just apply this equation. So power is 20 kilowatts. F, velocity is 5. So force is, if you divide this, 4,000. Force is 4,000 Newton. So the resistive force also should be 4,000 Newton. If this is 4,000 Newton, resistive force also should be 4,000 Newton. And at the second case, they say resistive force does not change. So still resistive force should be 4,000 Newton. It does not change. But the thing is, according to this equation, now the power suddenly increases, right? You have increases the power to 25. So you can see the minute the power is increased, force also increases. The velocity does not increase at once, right? It gradually increases. But at once the velocity does not increase. It gradually, it gains acceleration. And under the acceleration, its velocity gradually increases. But the moment, so you are applying this equation here for a moment, for the initial moment that the power is increased, right? So you need to find this F. So this is a case like that, right? For the previous ones, we just applied this for a time period, and when the velocity is constant. Here, they are asking about acceleration. Now the velocity is not constant. But for an instant, you can apply that. Initial moment, you are just applying this. At the initial moment, the velocity is still 5 meters per second. At the initial moment, right? Because velocity gradually increases. For the initial moment, you can say velocity is still 5. Then this F, that is the driving force, power is 25 kilowatts. 5 cancels off. Then the force is 5 times 10 to the power 3. So that is 5,000 Newton. Okay. So at the initial moment, you can see that force is 5,000 Newton. Now there's a difference. So you can apply F equals ma to find the acceleration. So the force here is 5,000, opposite side 4,000, mass is 1,000. Then the acceleration. So 1,000 acceleration is 1 meters per square second, right? So that is the answer, 1 meters per square second. Actually, this is the acceleration at the initial moment, okay? So you can do that. But there's something more that you have to understand here. Right. I'll explain that as well. So you know that it has gained this speed, right? Sorry, this acceleration. Why? Because it is increased, the power is increased to 25 kilowatts. And the driving force also increased. But if you analyze this equation, it is better if you can understand this, right? If you analyze this equation, now the velocity gradually increases. This is after the initial moment. I'm talking about this after the initial moment, what happens, right? So since it accelerates, velocity increases. Power is 25, it does not change. It is a constant. So if velocity increases, since the power is constant, let's say it is remained at 25 kilowatts, constant, the driving force decreases. So see that? This is the driving force. This starts to decrease. So if driving force decreases, unbalanced force decreases, meaning acceleration decreases, right? Acceleration is decreasing, but still the velocity is increasing. So further, F keeps decreasing, right? F keeps decreasing till this 5000 becomes 4000 and the acceleration becomes 0. Then after a while, it gains a constant velocity. So that's what happens there, right? Right. So the answer for that should be, that is something extra explanation. What could happen there? It's better if you can understand that, right? But for this one, you can just apply P equals Fv here and P equals Fv for the initial moment. For the initial moment. Right. Ninth case. When a boat with mass m moves at acceleration and is starting from rest, resistive force by the water is F. They say the resistive force is F. After time t, when the time is t, they say the resistive force is simple F. After t, power generated by the engine is, right? So this is the accelerating case, right? It is accelerating. So you cannot apply P equals Fv. But the thing is, you can apply P equals Ft for a moment of that motion. So the moment is when the time is t. You can apply that. So when the time is v, first let's find what's the velocity here. So the initial velocity 0. They have given the acceleration as a and the time is t. So this is the velocity, v equals at. Then you need to find the driving force, let's say capital F. So for that, I'll use F equals ma. So the unbalanced force is F minus simple F equals mass is m of the boat and acceleration is given as simple a. Then what is the driving force? F is equal to F plus ma. So this is the driving force. Okay. So we know the driving force and the velocity after simple t time. Then you can apply this equation in order to find the power. So applying this equation for a moment, right? This is not a constant velocity. You are applying this for a moment. Moment is when the time is t. So when the time is t, this is the force, this is the velocity. So the force is F plus ma, velocity is at. In order to get the answer, you need to keep t out and put a into the brackets. So this becomes mat. Then so the answer should be third one, right? AF plus ma squared times time. Okay. So this is the power in order for this to happen. Power required. So I just applied there. So you can see, so if you need to keep accelerating the object, you can see that you need to gradually increase the power as well, right? But for the previous questions, we didn't increase the power. We kept it at a certain level. So after a while, it gains a constant velocity. But for this question, they say it just keeps accelerating. So you can see, as the time goes, the power also has to increase in order to maintain this acceleration, right? Right, 10th question. Efficiency of a motor with power 800 is 60 watts. Waste of power of the motor is, right? So to find the efficiency, so this also is a really important concept, efficiency, that is eta is equal to output power divided by input power. Or it could be output energy, input energy, anything. But it has to be output divided by input times 100%. So I have to show this efficiency in terms of a percentage. That's why you have to multiply by 100%. right? So basically what they say is when you apply your input, depending on the efficiency, it gives us a output. Output can be equal to input, but it or should be less than our input, right? So let's say if you have a machine, so you provide it the input, then it provides the output. For the output, you can use useful energy, right? So if you get for an example, if you get like a bulb, let's say the bulb has 60 watt. So the bulb requires 60 watts to operate. But the thing is, the bulb does not use all that 60 watts to generate light. It generates heat as well, which is the waste. So let's say you provide 60 watt. It is printed on the bulb, right? This is the input. Then let's say as the light, you get like 20 watts, for an example, okay? Then the 40 watt is wasted as energy. So the efficiency of the bulb is, this is the useful power. So that is 20. Input is 60. They multiply by 100%. So 1 over 3, so it should be like 33.3% something, right? So that's the efficiency of the bulb. So this output means useful energy, useful power. Okay. So in practical cases, the output is always less than the input. There's no machine that can create, practically, we don't have a machine that has output that is equal to the input. Always it is some part of the energy is wasted, right? Right. We'll move on to the question. Right. So this is the equation. You know that 100% is 1, right? 100 divided by 100. You can write this or you can just neglect that when you are doing the questions if you want. They say efficiency is 60%. 60% means 60 divided by 100. So it is 0.6. So what they ask is output. Then the input is the 800. Input is 800. You need to calculate the output. So what do you get as the output? 800 times 0.6. 6 times, so it should be 480 watts. So this is the useful power, 480. So you provided 800 watts, you got 480 as the useful. So the wastage should be what? 800 minus 480. 0, 2, 3. 320 watts. So per second, 320 joule is wasted. Could be, it is wasted as, could be like heat, or could be like sound energy, like that. But the useful energy is the rotation, right? We use a motor for the rotation. So that energy is regarding 480. Right, 11th question. A pump with efficiency 50% lifts mass of water 700 kilogram in an hour to a height 100 meters. So let's find first that power thing. So water 7200. So I'm using mgh, right? Mgh divided by time. So mass is 7200, G is 10. To a height 100 meters within an hour. Hour means 3600. So 2 kilowatts, right? 3 zeros, 10 to the power 3 times 2. So you get 2 kilowatts there. So what is this? This is input or output? This is useful work, right? We use the motor to lift the water. So this is the power required to lift the water. So this is useful work or the power. So this must be output, right? Then just use the equation. So what they ask is input required. Okay. See, efficiency is given as 50%. 50% means 0.5. Output is 2 kilowatts. So what they ask is input. Just get input here. 2 divided by 0.5. 0.5 means half. Half flips, then it becomes 4. Right? So when you provide a 4 kilowatts as electricity to the motor, useful power of 2 kilowatts can be gained. So the answer should be third one there. Okay, next one. 1 kilowatt pump ejects water at 5 meters per second after lifting 300 kilogram of water to a height 10 meters within a minute. Efficiency of the pump is, right? Now they're asking about efficiency. Input is given, right? Input is 1 kilowatt. This is printed on the motor. This is provided by the electricity. So we need to find P out, output, useful energy. So they say 300 kilograms water is lifted and also given a velocity. So mgh plus half v squared. So this is energy, you need to divide that by time. So this is done within a minute, right? So you can find the useful power. So let's substitute. Mass is 300 kilograms, 10. Height is 10 meter. Plus half, mass is 300. Velocity is 5 squared divided by time within a minute. Within a minute means 60 seconds, right? So 65, this 300 can be, you need to divide this by both, right? 300. So here you get 500 plus, this is 5 times 25, 125 divided by 2, 62.5. So what do you get? 562.5 watts. So this is the useful, or we can call it P out. Okay. So to find the efficiency, P out is 562.5 divided by 1 kilowatt. That is 1000 watts. This is the input. When you provide the input 1000, useful amount is 562.5. Usually we express the efficiency as a percentage, so you multiply by 100%. Right? This 100 cancels off, then divide by 10. 56.25%. Right? So when I am doing calculations, notice that I am using the simplest way possible, right? I mean, someone can just calculate everything here, then divide by 60. Then it is going to be really hard, right? It's going to be really hard. When you just do all these calculation first, then if you divide by 60, then it's going to be hard. First, you have to divide by 60, then do this calculation. So you have to be smart about when you are doing calculations, right? Then the questions can be easy, right? It can be less complicated, right? Right, 13th question. When a boat with 150 kilogram is moving at 30 meters per second, power of the engine is 6 kilowatts. If the resistive force by watt is constant, distance that the boat moves after the engine is switched off, right? So before switching off the boat, it has both driving force and the resistive force. So I'll just apply equations here and find these ones. So P equals FV. So P is 6 kilowatts, 6000. This is driving force. Velocity is 30. So the force is 200 Newton. So we just found the driving force. So they say in this case, the boat is moving at constant velocity, right? So the resistive force and the driving force should be equal. Right. So at the second case, let's say now the engine is switched off. So what happens when the engine is switched off? There is no longer the driving force. Only resistive force is there. And they say it doesn't change, so it is 200 Newton. And the moment the engine is switched off, the speed is 30 meters per second. Right? So this is the initial case. So what happens now? Since the engine is switched off, the boat doesn't suddenly stops. It moves till the velocity becomes 0. And it decelerates, right? Only force is this one now. Right. So what they ask is this distance, it decelerates. Okay. So there are, you can use energy equation, so you can use F equals ma and motion equation. I'll just use the energy equation, right? Okay, so here the boat has a kinetic energy because of the speed. Then this resistive force eats up the whole kinetic energy. So we can write this as half mv squared. The kinetic energy of the boat is equal to work done by the resistive force, that is Fs. Right, half mass of the boat is 150, velocity is 30 squared. Right, equals force is 200 and it moves a distance s. Okay. So we have 75, here 900, 200 s, cancels off. 9 times 75, 45, 63, 67, then divide by 2, 3, 3, 7.5, yeah. So this much of a distance, the boat decelerates and it stops. Okay. Right. Next question, 14. Sands falls at 0.1 kilograms per second on a belt which moves at 2 meters per second. If the belt is kept running at the same velocity, what is the efficiency of the belt? Meaning the machine, right? There's a machine here. So you have to keep, you know that when you put sand here, you need to apply an extra force, let's say capital F, to maintain the velocity at 2 meters per second. Right? So for that, you need to provide power. Since it is constant velocity, you can just apply this equation. So the force is, force, you have to first find the force using this one. You know this equation, m v minus u divided by t. So m over t is rate of sand, right? That is 0.1. V minus u. So initially the speed of the sand to this side is 0. Then it gains the velocity of the belt after a while. So the final velocity of sand is 2. Initial velocity is 0. So you get 0.2 Newton. So this is the extra force you need to maintain the speed of the belt at 2 meters per second. Then you can substitute that force here. 0.2 times velocity is 2. So you need 0.4 watts in order to maintain it here, right? So what they ask is the efficiency of the belt. So this is the input power, right? So what is the useful or the output? P out or P useful? Here the useful energy is what we need is to accelerate, not accelerate, I mean to move the sand at this speed, giving sand a kinetic energy. So the sand would move with the belt, right? So how do you find that? The kinetic energy of the sand. Kinetic energy again, initial kinetic energy is 0, right? Divided by time. So this is half mass divided by time is m dot, mass rate, v squared. Half, so the mass flow rate is 0.1, v squared, v is 2, 2 is squared, so that is 4. So you get 2, 0.2. So you have 0.2 watts. Right, then you need to find efficiency. So this is P in, right? P out divided by P in times 100%. So P out is 0.2, P in is 0.4 times 100%. So 1 over 2, so it is 50%, right? So that is the efficiency of the belt. That is 50%. Right, 15th. While a machine does useful work 50 joule, energy wastage is 30 joules. Find the efficiency of the machine, right? So let's say this is the machine. The useful work or the output is 50 joule. This is useful, right? Or the output. 50 joule and the wastage is 30 joule. Right? So the input should be what? It should be waste plus output, right? So input should be 80 joule. So what they ask is efficiency. Output divided by input 100%. So the output is useful, that is 50. Input is 80, 100%. So 5 divided by 8, what do you get? 0. So for 50 it is 6, right? 48, 2, 4, 8, 5, 100%. So multiply by 100, so it is 62.5%. Right? So this is the efficiency, 62.5%. So there you just have to identify what are the inputs and outputs. So the input should be waste plus output, right? Waste plus output is equal to the input.